Breath.
Hello, everyone. Today we are going to continue chapter 5 and move to section 5.3, where we consider several examples of non-polynomial functions and coefficients in linear equation of second order, and see how series solution is going to work for them and how we deal with series solution. Also, we are going to consider what happens when we deal with singular point. We're not going to search for solutions at singular points, but we are going to define radius of convergence of solutions at ordinary points. But this is going to be like second part of the lecture. First part is going to be examples. So we are going to start with example number 1, and that's going to be differential equation with non-polynomial coefficients. So give me a second. So it's too thick, I guess. I'm going to move to this one. And example number 1, differential equation with non-polynomial coefficients. So I think that's supposed to be us also over here. So what I mean by non-polynomial coefficients, let's look at this equation. Second order derivative of y plus cosine of x, y equals to 0. Let's search for general solution at x equals 0. And we're not going to find actually the whole series. Let me put at x equals 0. We just need to find first 3 terms in each y1 and y2 series solutions. Well, you remember what are y1 and y2, right? They are two linearly independent solutions. So what is new in this equation? The new thing in this equation is cosine, right? Cosine is not polynomial. Not polynomial means that it does not look like 1 plus 2x plus 3x squared and something like this. So normally when we search for series solution, we don't want to have non-polynomial functions in our equation because the idea is to represent everything as a polynomial. And if something is non-polynomial, it's not going to work. What are we going to do with cosine? We are going to represent cosine, represent as a series. As a series. Well, because we are looking for a solution at 0, we are going to represent it as a series at 0. So cosine of x, you probably remember somewhere in the beginning of chapter 5, I was telling you that cosine is what? 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial and so on, right? So it's going to have even powers of x. Well, there are more powers. I just put like first 4 terms because I think that's going to be enough, but maybe I'm wrong. Now our cosine is not cosine anymore. It's just a polynomial. Yeah, infinite polynomial, but the series we are searching for are infinite too. So let's start to look for solutions. So we are going to look for solution y, which equals, I'm going to expand the series because I'll need only first 3 terms. I'm not going to deal with sigma notation just because of this, because I need only first 3 terms. I'm going to deal only with expanded form. So it's C0, C1x, C2x squared, C3x cubed, maybe C4x to the power of 4. I don't know, let's do one more, C5x to the power of 5. And you understand that you always can add more terms over here if you need it for your solution. So again, you can represent it as sigma notation, but not necessary just because we look for a certain amount of terms. I'm going to do the derivative and the second derivative. We don't need the first derivative here, but without it, we're going to not find the second one, right? So I differentiate it once, and C0 is going to disappear, and that's C1, which is left over from the first term, and 2C2x plus 3C3x squared, right? I differentiate all these power functions, plus 4C4x cubed plus 5C5x to the power of 4 and more terms. And the second derivative, C1 is going to disappear. Right here, we are going to have 2C2, and there is no x, plus, well, if I differentiate x squared, it's going to give me 2x. So I'm going to have 6C3x. Again, I'm multiplying everything because I'm not planning to get a general solution. So I just need numbers and the coefficients. Here I'm going to have 4 by 3 is 12, right? C4x squared, and 5 by 4 it's 20, C5x to the power of 3. So that's my second derivative, and I'm ready to plug everything into my equation. Remember that cosine is going to be plugged as a series too. Okay, so my second derivative, well, unfortunately, there is no other way than just to copy everything and hope that you don't lose anything. So 2C2 plus 6C3x plus 12 C4x squared plus 20 C5x cubed plus, I'm going to put 3 dots, and then we'll need to do cosine. Well, for cosine, guys, I don't know how many terms I'm going to keep, just 3, okay? If I keep all 4, it's gonna be like not fitting into my screen. Well, 2 factorial is 2, so I'm not going to pretend that I don't know this. And plus x to the power of 4, and I don't know what is 4 factorial, so I'm going to keep it. I'm going to put lots of dots, and then copy the second derivative. 2C, oh, the function, actually, I already did second derivative, the function. Why? Where is my function? Okay, C0 plus C1x plus C2x squared plus C3x cube. I'm going to stop at x cube because my screen is running out, but actually supposed to be more terms, and you always can add them if necessary. Now, what I'm going to do, I'm going to find the coefficient in front of x to the power of 0. Well, you know that there is no x to the power of 0, so basically the coefficient which does not have any x, right? So start with this one, and that's 2C2, and then for this part of the equation, we have 1 multiplied by C0, so I'm going to have C0. Do we have any other coefficient without x? Well, if we multiply 1 by C1x, it's going to have x, right? If we multiply x squared by C0, it's going to have x squared. So there is no other coefficient. So I'm going to set it to 0 and kind of calculate C2. C2 is going to be minus C0 over 2. Yeah, that's gonna be super boring for next like 10 minutes, I guess. X to the power of 1 is going to be like 6C3, right? That's the term with power of 1. And over here, do we have term with power of 1? Well, if I multiply 1 by C1x, I'm going to have power of 1, right? So it's a C1. Can I obtain any other power of 1? Like if I multiply x squared by C0, it's going to be a square. So there are everything else, though it's an infinite series, everything else is going to have powers greater than 1. I just like imagine that you multiply literally the terms. Okay, so equals to 0, from where C3 equals minus C1 over 6. Okay, I'm just going to do 2 more. Don't worry too much. It's not going to take forever. Well, again, because I'm asking just limited amount of terms in my final solution. So for x squared, I'm sorry, I'm going to have 12 C4, this is x squared, right? Now, what I have for x squared in this part? First, if I multiply 1 by C2 and x squared, I'm going to get x squared. So that's going to be plus C2. Second, if I multiply this minus x squared over 2 by C0, I'm also going to have x squared. So it's going to be minus C0 over 2. Remember, we don't copy x squared because we kind of take it outside of parentheses. And set it to 0, which is going to give us, sorry, press the eraser, So which is going to give us C4 equals C0 over 2 minus C2, and we need to divide it by 12, right? Well, I'm guessing I'm going to substitute C2 already because I do know C2. So I'm going to write down C0 over 2 minus, and C2 equals minus C0 over 2. Well, kind of strange, but possible. Well, if we have minus and minus, it's plus, and C0 and C0 is going to give us just C0. So it's C0 over 12. Very good. So I'm just going to do one more. Maybe we'll need more, but we're going to see, guys. So for cube, we have 20C5. Do we have cube from here? Okay, let me look over here. So I don't have, I have cube, which is going to be 1 multiplied by C3x cube, right? So I'm going to kind of add C3. Do I have any other C cubes? Well, if I multiply 1 by anything else here, it's going to give me greater than cube. Now, I'm going to start multiplying x squared. If I multiply it by the first one, it's a square, right? Multiplied by the second one, it's going to give me x squared by x cubed, right? So it's going to be minus C1 over 2. If I multiply x squared by the next term, like with square over here, which does not look like a square, it's going to give me already fourth power. So I'm kind of fine here. Well, I think that's all I have for the cube. So now I'm going to solve it for C5, which is C1 over 2 minus C3, also divided by a weird coefficient of 20. Well, we already know C3, that's C1 over 6, so I'm going to plug it in. So it's C1 over 2 minus C1 over 6 and divided over 20. So common denominator here is 6, right? I multiply it by 3, and I'm going to have 3C1 and plus 1C1, it's 4C1. And here 6 and 20, right? And if I cancel like 4 and 20, I'm going to get 5, and that's C1 over 30. I just did math and multiplied everything. And well, you can continue, and it's going to be super boring. So I'm just going to plug whatever I calculated already into my series. Let me scroll it up. You remember that series is always looking same. So the series is going to look like this. Y equals C0 plus C1x plus C2x squared plus C3x cubed. This series is not going to change unless you change that center of the series. So if you center it at 0, it's always going to look like this. So guys, I'm going to start. Maybe I should write down like few more coefficients. C4x to the power of 4, maybe C5x to the power of 5. You know, I'm going to start plugging in my C's. So for C0, there is no equation on C0, and C1 is C1, right? But for C2, we do have expression. Let me find it. It's somewhere up. C2 is actually minus C0 over 2 and multiplied by x squared, right? C3, which is before x cubed, is going to be minus C1 over 6 x cubed. And C4 is going to be C0 over 12 x to the power of 4. And C5, I think that's the maximum we found, right? We found just C5 coefficient, is going to be C1 over 30 x to the power of 5. And of course, some other terms. What I'm going to do now, guys, I think I'm going to unify terms with C0 and terms with C1 in different parentheses. So C0, sorry. So C0 over here, very typical mistake. People take C0 outside and don't give anything inside. So it's 1 here, right? And over here we have minus, well, remember, you take C0 outside, so there is going to be no C0, but it's x squared over 2, right? Any other C0, okay, plus x to the power of 4 over 12, plus some other terms which we did not calculate. C1, we have x left, right? C1 is minus x cubed over 6, and C1 plus x to the power of 5 over 30, and some other solution, some other coefficients. Okay, well, we were lucky and we got exactly first three terms. So this is my y1 and it has three terms. Three terms, 1, 2, 3, right? And this is going to be my y2. Also, first three terms. And again, if you kind of continue the process of comparing powers, you can get as many terms as you need. It's just like, that's how many we were asked to do. And sometimes it's even not necessary to do that many. Normally, guys, no one is asking you for exact solution. Usually you will need an approximation. And this is good approximation, first three terms. Maybe you even will need like 2 terms. So we finished the problem. You can write down that y1 equals, my 1 doesn't look like 1 actually. Y1 equals 1 minus x squared over 2 plus x to the power of 4 over 12. So first three terms, that's kind of, final answer. X minus x cubed over 6 plus x to the power of 5 over 30. How do we calculate C0 and C1? We calculate them from initial condition. I'm going to write it down somewhere. So C0 and C1 are calculated from initial condition. Well, right now I did not give you any initial conditions, so you don't calculate them. But if you are given initial conditions, okay, you can calculate actual coefficients and get like solution without kind of separating on two functions. Okay, very good. And I'm going to move to my next example. Why don't I use blue color? But I want to be sure that I'm using the smallest print. Okay, moving to my next example. So we know how to deal with coefficients which are non-polynomial. Now, example number 2, let's learn how to find a solution of differential equation when you do have the right side, non-homogeneous equation, but it's not polynomial right side. Again, you see exponential function, non-polynomial. What is like searched here? Find first two terms in both series solutions. So I'm going to write it down so I don't forget. Find first two terms in both series solutions about 0. So again, we are considering series solution about centered about 0. Well, again, you can use the same idea we used for coefficients, right? We do have exponential function. We can represent it as a series. So start representing exponential function as a series, which is 1 plus x squared over 2. It's supposed to be 2 factorial, but, well, we just kind of can write down over 2x cubed over 3 factorial, which is 6, and so on. So put this series into your equation and kind of search for series solutions. So look for y as a series solution, C0, C1x, C2x squared, C3x cubed, maybe kind of C4x to the power of 4. I don't think that we need that many. Guys, you see that I'm doing all examples and I always do not use series notation. Why? Because I need just first few terms. I don't need a general formula. So if you are not planning to get a general formula, if you just need like few coefficients, it's much faster to just kind of write down expanded variant of the series. Okay, I'm going to do the derivative over here because we'll need to differentiate it, and that's C1 to C2x. By the way, derivative never changes too. The series never changes too. That derivative never changes too. For C4x cubed. And yes, guys, if you understand how the second derivative looks, you don't need to do the first one. 2C2 plus 6C3x plus 12 C4x squared, and so on. Okay, now I'm going to plug my second derivative, my function, and my exponential function into my equation. I don't want to move it. So 2c2 plus 6c3x plus 12c4x squared plus some other terms plus like actual series, original c0, c1x, c2x squared, c3x cube plus some other coefficients and exponential function 1 plus x squared over 2 plus x cubed over 6 and some other terms. Well, again, if you did not write enough terms here, you can always kind of add more terms while you feel that that's not enough terms for coefficients. Now we are going to do same. We are going to combine coefficients in front of different powers. That's what I'm going to do. So I'm going to start with x to the power of 0 as usual. So on my left side, I have 2c2 and c0, right? On my right side, I have 1. Well, here I'm going to find that c2 equals 1 minus c0 over 2. Okay, very good. X to the power of 1, and I have 6c3 plus c1 equals, again, 1. Well, just because the coefficient is 1. So what I have c3 equals 1 minus c1 over 6. Okay, next one is x squared. And I have 12 c4 plus c2 and equals, well, for square is 1/2, right? 1 over 2. So from where c4 equals 1 over 2 minus c2 divided over 12. I think I'll need to work a little bit on this expression 1/2 minus c2. I do know c2, right? So I'm going to substitute it here. So it's 1/2 minus, instead of c2, I'm going to put 1 minus c0 divided over 2 and divided over 12. I'm hoping to simplify it a little bit. So I have 1/2 and minus 1/2 here, which are going to cancel each other, right? And I'm going to have just c0 over 2 and over 12. What happened to minus? Well, there was minus and minus, which disappeared, right? Maybe I'll need more, but I'm hoping that I won't actually. So I'll try to plug everything into my series solution. If I already have first two terms for each solution, I'm just going to be happy and I'm not going to continue because, well, you know, it's always like time taking. So again, series y, c0, c1x, c2x squared, c3x cubed, c4x to the power of 4, and some other terms. Because I did not calculate more, I'm going to just limit myself to c0, c1, c2. So c0 is going to be just c0, right? c1 is going to be just c1. For c2, we have the formula, and it's 1 over 2 minus c0 over 2 and by x squared, right? For c3, we also have the formula. I don't want to make it smaller. I want to put it like this. Yeah, just don't see the where's my c3. Okay, I'm going to just scroll it a little bit up. So plus, okay. Plus 1 over 6 minus c1 over 6 and x cube over here. And you know that coefficient 3 is going to stand in front of x cube, so kind of a checkpoint. And the last one, I guess, c4, which is c0 over 24x to the power of 4. Okay, very good. Now, guys, I'm going to start separating coefficients using the constants. So c0, 1 here, right? Do I have c0 more? Yeah, I have minus x squared over 2 Do I have any C0 more? Yeah, I do have actually. I have this x to the power of 4 over 24. And I don't have more. Now, next one, C1, and I have x. C1 minus x cubed over 6, and no more C1, so I'm going to put lots of dots. And I have leftover. What is my leftover? Leftover is 1 over 2x squared, x squared by 1 over 2. And over here leftover is x cubed over 6, right? If I multiply this 1 over 6 by x cubed over 6. And kind of lots of other coefficients, right? So what I have, guys, I have slightly different situation from what we had before. I got my y1, and I even did more terms. I was supposed to calculate first 2 terms. I calculated first 3 terms. I got my y2, and they are solutions of homogeneous equation, right? Linearly independent, everything fine. What is this? Well, guys, remember that normally if you solve non-homogeneous equation, solution is a sum, so sum of solutions of homogeneous equation with arbitrary constant plus a particular solution. So what we got over here is a particular solution of our equation. And well, it means that if you kind of take this function and differentiate it, plug it into equation, it's going to solve non-homogeneous equation. These two solutions are going to solve homogeneous. The first one and the second one. Okay, well, good. So that's how we solve problems if functions are not polynomial. Again, mostly we are going to have polynomial, but non-polynomial functions not supposed to stop you from solving it by series, right? Now, guys, I'm going to explain you some theory. It's kind of boring, but very, very useful. And eventually, if you deal with serious solutions, of course, you can open the book and read more about this. But just like, you know, that something sticks in your head and going to kind of maybe question your answers if you kind of solve anything. And of course, you probably are not going to remember very much from the theory I'm explaining, but maybe in a while you can just read a little bit more. So this is very basic theory. Okay, theory. Useful, but boring. Should I erase this? Yeah, boring is not our word, right? So I'm going to just erase everything. Okay, we're going to start with definition. So let me put theory. And we start with definition. Definition. A function f of x is analytic at x equals a, so not necessarily 0, if it can be represented as a power series in powers of x minus a with either positive or, sorry, instead of or infinite radius of convergence. Okay, I'm not very good in writing down on the touch screen. I'm going to just maybe give several examples. For example, e to the power of x can be represented as 1 plus x squared over 2 factorial plus so on. So it's represented at x equals 0. Remember, this is Maclaurin series or Taylor series at x equals 0, and a radius of convergence here is equal to infinity. You can just use the ratio test and kind of find out. Well, we did it in calculus 5b. I don't have time to do it again. Let me. Okay, stretch it a little bit. Somehow the whiteboard does not obey me. Okay, sine of x, another function, sine of x, which is x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus and so on. Also at x equals 0 has a radius of convergence equals to infinity. ln of x is not analytic at x equals 0. Why? Question. Why? Because it's undefined and has undefined derivatives at x equals 0. Well, you probably remember that logarithmic function looks like this. And at x equals 0, it goes to infinity. And it's kind of undefined over here, right? We don't have any ln of 0. And derivatives are also undefined. So this one is not analytic. And first two are analytic. Analytic are good, non-analytic are kind of not very good. Well, it's not necessary. So how about other points for ln of x? For example, is ln of x analytic at point 1? For example, ln of x at x equals 1. Is it analytic? Yes. It has actually series representation. I'm going to give it a little bit later. We had it in also calculus 5b. So at point 1, the function is defined, it equals to 0, and all derivatives are defined, and like everything is fine. So it is analytic. Yes, analytic. So when you talk about the analytic function or non-analytic function, it's always where. It's not like just, but a function cannot be non-analytic anywhere because like if it's undefined everywhere, or so normally you expect to be non-analytic function somewhere and analytic somewhere. Well, okay. More on definition. Let me scroll it up. Okay. Definition. A point x equals x0 is an ordinary point of differential equation if both p of x and q of x are analytic at x0. And when I'm talking about p of x and q of x, I'm referring to the differential equation which look like this. Second derivative of y plus p of x, y first derivative plus q of x, y, and equals to 0. So the coefficients of this second order differential equation are analytic, then the point is ordinary point. Definition. A singular point x equals x0 well, actually I was trying to say that the point is not ordinary, is not ordinary. So if the point is not ordinary, we call it singular point, just like definition from inverse. Okay, couple of examples. Example number 1, y prime plus y equals 0. Do we have any singular points? No, no singular points. All functions are continuous. Well, you see there are coefficients like 1 and 1. They're obviously continuous, right? Example 2. Second derivative of y plus e to the power of x, first derivative of y plus sine of x, y equals to 0. Well, we know that this one is analytic. And this one is analytic. Sorry. Analytic. So everything is like, and they are analytic about any point, and the radius of convergence is infinity. So function has no ordinary points too. No singular points too. So all points are ordinary, right? Next, let me go back to black. Example number 3. Second derivative of y plus x, first derivative of y plus ln of x, y equals to 0. Is it analytic at point x equals 0? Question. Well, p of x, the coefficient of first derivative is x, and it's already a series. It doesn't look like a series, but it's a very short series. A series, short one, just one term series. Okay. Q of x, ln of x. We already know that ln of x is non-analytic at x equals 0. Non-analytic at x equals 0. Cannot represent it as a series. Can be represented as a series. Yeah, unfortunately, it's not analytic at point x equals 0. So we are going to make a conclusion that x equals 0 is a singular point. Of differential equation. Okay, next example. Example number 4. X, second derivative of y plus y prime plus x, y equals to 0. Well, this equation is not exactly looking like second derivative plus p plus q. So we are going to move it to the standard form. We are going to divide by x. X, y prime plus y equals to 0. I divided the whole equation by x to get rid of the coefficient of second derivative. Okay, you see that this one is undefined at x equals 0. So x equals 0 is a singular point. Well, 1 over x is undefined because it's just like, the function which is like undefined. Okay, now we are going to move to polynomial coefficients. For polynomial coefficients, we are going to have a very nice theorem. So now polynomial coefficients. I'm going to write them down as P of x, Q of x, and R of x. You see that they're capital letters because I want to make a difference between this PQ, which we had before, and these ones, which are PQ and R, the polynomial coefficients. So for them, if P of x0 is not equal to 0, we are going to say that x equals x0 is ordinary point. And I'm going to write down the equation. I'm sorry, I was supposed to write down the first equation. Somehow missing it. Let me add equation over here, okay? I'm thinking like I don't want to erase anything. I'm going to write it down, okay, below. P of x, first, second derivative, Q of x, first derivative, plus R of x, a function. So we are considering equation looking like this. Sorry, and the coefficients are polynomials. And if P of x 0 is not equal to 0, then this point is going to be ordinary point. Well, just imagine that you divide by p of x to get a standard way to represent the equation, and in denominator you are going to have p of x. Of course, if p of x is not equal to 0, then you are going to have like this polynomial over this polynomial over this. But if it's not a special point, we are not dividing by 0, it does not go to infinity, it's a defined, and everything is okay. Now we are going to write down that p of x0 is equal to 0. Then x equals x0 is a singular point. Okay, let's consider a couple of examples. Example, x squared minus 1, second derivative, plus x prime minus y equals to 0. Well, you see that my p is this. This is my p of x. If I set it up to 0, I'm going to see that x squared minus 1 equals to 0 has two solutions. X equals plus 1 and minus 1, right? So these are singular points. The equation. Well, again, normally we divide by this, and we are going to have x over x squared minus 1, and at which points the function is undefined, okay? It's going to be undefined at x1 and x negative 1. Well, I'm not proving this statement about the points. If you wish, you can look up in the book. It's not very difficult to divide polynomials and like prove everything, well, like considering general polynomials. It's just going to be time consuming. Now, guys, how singular points are going to help us? We are not going to look for solutions at singular points, though it's possible. It's going to be like next sections, like section 4, 5, 6. We are going to use singular points to find the radius of convergence. Singular points and the radius of convergence of power series solutions at ordinary points. Yeah, guys, now we are going to have a very nice theorem. I don't want to write down the theorem because I hate writing on touch screen. So I already prepared it somewhere on my whiteboard. I'm just going to try to copy it over here, but I'll need to do a little procedure of doing this because I already wrote, you see how much, but the theorem sits over here. I'm going to copy it. I don't know, I'm not sure that didn't copy it. Okay, let's hope that it did. And pass it over here, okay? So, okay. It worked actually. Just I'll need to move it to kind of to sit next to the rest of my lecture. Let me make it a little bit longer. So a very nice theorem, which I'm going to finish actually. I just prepared the text. So the theorem, existence of power series solution, and I'm not going to prove the theorem, but I'm going to explain what is what in this theorem. If x equals x0 is an ordinary point of second order linear differential equation, we can find always two linearly independent solutions in the form of power series centered at x equals x0. And they are going to look like, let me write it down, sigma Cn x minus x0 n goes from 0 to infinity. So these are going to be like theorem tells that if you have ordinary point, then solution, and the two of them exist. And what else? This series solution which exists is going to be convergent at least on some interval defined by inequality x minus x0 less than r, and this r is going to be the distance to the closest singular point. That's where singular points are going to help us. So theorem is going to help us to answer the question, what is minimum radius of convergence of the series you found? For example, you solve equation, you find the coefficients, and there are two series, y1 and y2. They both solve the equation, general solutions, right? Now, where they are convergent. Sometimes it's going to be hard to check because there is no general formula. But this theorem is going to help us to predict the minimum radius of convergence. Minimum means that it can be greater, but it cannot be less. Okay, just like I'm going to consider maybe example or two examples of doing this. So example, I'm going to write it down. Find minimum radius of convergence for a series solution at x equals 0. And equation is going to look like this. X squared minus 1, y second derivative, xy first derivative minus y equals to 0. Well, basically what I did, I just copied the equation I had before in an example, right? We already know that x squared minus 1 equals to 0 is going to have two solutions, x plus minus 1, and they are singular points. Right? Theorem tells us that the radius of convergence is going to be the distance to the closest singular point. Well, how to find this distance? First, we are going to graph this point where we search for a solution center of my series, and x equals 0. X equals 0, right? Second, I'm going to graph two singular points. That's minus 1 and plus 1. I'm going to label singular points. Points. Okay. Center of series. Now, what is the distance? Well, lucky or not, but the distance to each of these 2 points, not necessary, but can happen, is equal to 1 unit. So the distance equals to 1. Again, we were placing our center of the series symmetrically to the singularities, to singular points. But it's not necessary. If you consider x equals, for example, 5, the closest point is going to be this one. Okay? And the distance is going to be what? 5 minus 1 equals 4. So I'm just trying to show you how to calculate the distance. So this distance is going to be the radius. So the radius is equal to 1. Again, in this problem, they're not asking us to find the series. They're asking us to find the radius of convergence. So that's what we did. A very short question, right? Again, read the question carefully. Sometimes you will need to find the series. Sometimes you just need to find the radius. Okay, I'm going to consider one more complicated example. Let's say 2, and let's call this example 1. Example 2. Example 2 is going to have more complicated coefficient. X squared minus 2x plus 5. Second derivative plus x y prime minus y equals to 0. Okay, we have more complicated coefficient over here, right? And we are like trying to find the series at point x equals 0 and x equals 1. We kind of consider two different series, and we're trying to figure out like what is going to be the radius. First, we are going to solve equation x squared minus 2x plus 5 equals to 0, because this is my big P of x, right? And this equation has two solutions. X1 and 2 equals what? Plus minus square root of 4 minus 20. 5 by 4 is 20. And plus 2 divided over 2. Well, here we are going to have plus minus 4i plus 2 over 2, or 1 plus minus 2i. Two complex solutions. How should I deal with distance if I have complex solutions? Well, watch how I do this, and you can do it the same way. You draw number plane, and that's going to have real axis and imaginary axis, and you graph these two singularities on this number plane. For example, this is 1 and this is, okay, 1 is too far, I guess. I'm supposed to write it. But this is 1, this is 2, this is 1, and this is 2. So my singularities are 1 unit on a real axis and 2 units on imaginary. So what's my singular point here and my singular point here? Imaginary part is plus minus, right? I should make them red to kind of have it the same way I was doing this. Now, where is my center? Let me do the center in the green too. My first center is x equals 0. So x equals 0 sits over here, right? That's totally real number. So what is the distance for x equals 0? I'm going to label x equals 0. Well, we just need to calculate this distance. And the distance is going to be just graphically, you can calculate it's a square root, right? The distance between 0 and 0.12 is going to be 1 squared plus 2 squared, which is going to be a square root of 5. And that's the same distance to both points. So the radius is going to be 4x equals 0. The radius equals a square root of 5. I'm going to change my color. I don't know. Let's make it blue maybe. And draw my second point. My second point is x equals 1. So I'm going to graph my x equals 1. And I see that for x equals 1, this point is kind of far away. And the closest point is this. What is this distance? Well, you kind of look at the picture and see that distance equals 2. So I'm going to write down distance equals 2. So the 4x equals 1, the radius equals 2. Again, my suggestion, always look at the graph. Okay, and you can use standard like distance formula. Just remember, coordinates of this point are what? 1, 0. And coordinates of this point, for example, is 1, 2. So find the distance between these 2 points, but you are going to get the same answer. Okay, a little summary on how to find singular points. Summary. On singular points. A, if P, Q, and R are polynomials, then set up P of x equals to 0 and solutions are singular points. Are singular. B, not always like this, right? If P of x, a little coefficients, or Q of x, if P of x or Q of x are undefined, oh, sorry, it's not supposed to be here. How do I kind of, Q of x are on, not both, can be just one of them, or their derivatives. Then x equals 0 is a singular or undefined. I think I'm supposed to say here at x equals x0, because I moved it on this side. If either of them is undefined at x equals x0, or some derivatives of there are undefined, means that you cannot make a series, Taylor series, then x equals 0 is going to be singular point. This works for non-polynomial. I'm going to put it here. Works for non-polynomial P of x and Q of x. Okay, that's all I wanted to explain in this section. And we're going to finish at this point. I'm sorry that it's like a long lecture. Okay.